In today's video, we're going to be talking about the physical properties of alkanes, cycloalkanes, alkenes, and alkynes, as well as the nomenclature of cyclic and aromatic compounds. Alkanes, which are just straight-chain saturated hydrocarbons, saturated means that your compound has no double or triple bonds and it is only single bonds. So alkanes are always saturated hydrocarbons. Same with cycloalkanes. Cycloalkanes are the same thing, but they are in a ring. This is a six-membered carbon ring. And recall that the prefix for six is hex. And if we're naming it as an alkane, it would be hexane. But this is a ring, so it's a cyclohexane. This is a three-carbon ring. So it's a cyclo, then the prefix for three is prop, and ane because it's an alkane, so cyclopropane. At room temperature and 1 atmosphere pressure, alkanes and cycloalkanes exhibit the following characteristics. These compounds are usually colorless. As a gas, they will be transparent. As a liquid, they'll be clear. And as a solid, they'll be white. They're also usually pretty smelly. When we talk about the boiling point of this compound, remember boiling point is when something goes from a liquid to a gas. The boiling point is a measure of how easy or hard it is to break the bonds holding your compound together in order to change it from a liquid to a gas. With these compounds, the longer the chain or the higher the molecular weight, the harder it is to break the bonds and boil the compound. So the higher the boiling point, like this one down here. We also have to look at the compactness of the shape. A more compact shape will have a lower boiling point. For example, take a look at this shape versus this one. They both have 5 carbons, but this shape here is a neopentane, and this is just pentane. Although they have the same amount of carbons, neopentane is more compact than pentane. So it has a lower boiling point at just 9.5 degrees Celsius, whereas pentane's boiling point is about 36.1 degrees Celsius. Now let's take a look at the melting point. Melting point is when we have a solid that changes into a liquid. There are a couple different factors affecting the melting point of these compounds. The longer carbon chain we have, such as this one down here, the higher the melting point, because it's harder to break those bonds to change it from a solid to a liquid, just like it was with boiling point. However, melting point also changes with the compactness of our shape, but in the opposite trend that boiling point did. Say we have, again, neopentane and pentane. The melting point of neopentane is higher at negative 16.6 degrees Celsius, and the melting point of pentane is lower at negative 129.8 degrees Celsius. This is because the more compact the shape, the higher the melting point. So the melting point of neopentane is closer to a positive number than the melting point of pentane because it's a more compact shape. The reason for this is because the surface area of our overall molecule decreases and it makes the shape more dense, which causes the melting point to increase because it's harder to break it apart. The symmetry of the molecule also plays a role in our melting point. When compounds are more symmetrical, there are fewer spaces between the atoms of that compound, and the melting point is higher than if you have a shape that's not symmetrical. And this applies to the same example. So although neopentane and pentane are both symmetrical molecules, if we cut pentane down the middle here and we cut neopentane down here, you would see that they're symmetric on both sides. But because neopentane is also more compact, the melting point is higher. Now moving on to solubility. Alkanes are nonpolar compounds, so they would be soluble in nonpolar solvents, something like acetone, but they would not be soluble in water or any other polar solvents. Now let's take a look at alkenes. Alkenes are compounds with double bonds in them. Alkenes are usually smellier than alkanes. Ethylene, for example, is known to have a bit of a musty odor. Now let's talk about melting point. So the melting point of a cis-alkene, if you remember cis, means that the higher priority groups on either side of the double bond are going in the same direction. So both of these are going down, and that would be a cis-alkene. With a trans-alkene, the higher priority groups on either side of the double bond are going in opposite directions. Cis-alkenes have a lower melting point compared to trans. This is because cis-alkenes cannot pack together as tightly as trans-alkenes can, so it takes less energy to melt them. Now, when we talk about polarity, the polarity of an alkene is more than that of an alkane because we have these electrons in the double bond, which are slightly more reactive. So when we look at the dipole moment of a cis-alkene versus a trans-alkene, recall that each of these points is a carbon. So these pi electrons, or the 2 electrons in the double bond, are polarizable, meaning that they contribute to an instantaneous dipole moment. So although you have a carbon-to-carbon bond here, you would think that it's not polar, but because you have these double bonds here, the dipole moment is actually going to go towards the double bond. And here, the dipole moment in this carbon-carbon bond is going to go up towards the double bond, and over here it will go down towards the double bond. In this trans-alkene, because we have one dipole moment going up and the other one going down, the net effect is 0. So the net sum of both of these dipole moments is one that points upwards. So cis-alkenes have a positive dipole moment in the direction of the double bond. But in general, because of these pi electrons, the electrons in the double bond, alkenes are more polar than alkanes. Now let's take a look at alkynes. Alkynes are compounds that have a triple bond. An alkyne is made up of 1 sigma bond and 2 pi bonds to make up these 3 bonds. Many of the properties of alkynes are the same as alkanes. However, the boiling point, going from a liquid to a gas, is a bit higher than that of alkenes because now we have a triple bond instead of a double bond. Alkynes are usually odorless and colorless, aside from ethylene, this 2-carbon triple bond, which has a slight odor. When we talk about the phases of alkynes, any alkyne that has up to 3 carbons is going to be a gas. Anything that has 4 to 11 carbons is going to be a liquid, and anything higher than that, so 12 carbons or more, is going to be a solid phase. Now let's talk about the nomenclature of cyclic and aromatic compounds. So what is a cyclic compound? A cyclic compound is any compound that is in the shape of a ring. So it is closed on both ends. It can't be left open like this. We can have cyclic compounds that have double bonds in them. They can have other substituents coming out of them, and so on. Now let's talk about aromatic compounds, because cyclic compounds can exhibit something called aromaticity. When we have regular cyclic compounds like these examples, where we don't have any other functional families, but they're basically just alkanes, but in ring form. These are cycloalkanes. But they can exhibit something called aromaticity, and then they become aromatic compounds, which is a type of cyclic compound. Aromaticity means that we have a conjugated system with delocalized pi electrons rather than alternating double bonds. It looks like we have 3 double bonds alternating at each carbon. But in fact, this is a conjugated system with delocalized pi electrons rather than alternating double bonds, and that is why we get aromaticity. Well, every double bond has 2 electrons, and these are called the pi electrons. When they're delocalized, they don't belong to a single atom or bond, but rather they belong to the whole group of atoms. So these pi electrons in the double bonds are actually resonating between the atoms in the conjugated system. This is actually benzene here, and it can be drawn with a circle in the middle because these double bonds resonate back and forth so fast. But let's talk about what exactly is conjugation, and how do we know if a system is conjugated? Conjugation is a system of 3 or more overlapping p orbitals. I gave you the example of benzene, but there are many more conjugated systems that can also exhibit aromaticity, or they might be straight chains. When we look at a double bond, for example, ethene here with 2 carbons, let's look at the pi bonds in a double bond. Pi bonds look like this, and there's one for each carbon, and they overlap. So if we draw the pi bonding in our carbon-to-carbon shape, these are called p orbitals. And the bond that's formed when these p orbitals are overlapping, which happens when we have double bonds. But pi bonds are also present in triple bonds, alkynes. When we have a conjugated system, we will have 3 or more of these p orbitals overlapping on adjacent atoms, so they have to be next to each other. Let's look at a shape like this. When we draw in the p orbitals for each of these double bonds, the bonding is occurring over here. However, between these adjacent p orbitals, there is a little bit of overlap, and that makes for a conjugated system. So these are 3 or more, these are 4 p orbitals, and this would be considered a conjugated system. It doesn't always have to be 2 double bonds though. Let's take a look at other examples when we can have a conjugated system. For example, if we have something like this, there are pi electrons in this double bond, and then we have a positive charge, a carbocation, on the next carbon over. Although there are p orbitals on this double bond that are overlapping, there is an empty p orbital on this carbocation here. And because of that, it actually does count as a conjugated system. Another example is if we had something like NH2 with a lone pair on it. The p orbital from nitrogen contains a lone pair, and that also counts as part of a conjugated system. So these 3 p orbitals would count as a conjugated system. Now suppose we had a CH2 group with 1 electron on it, which is a radical. This p orbital with a radical in it also counts as a system of 3 or more overlapping p orbitals, and can also count as a conjugated system. So these 3 examples that I just showed, along with the example of adjacent double bonds, will all count as conjugated systems. Here's an example of when we don't have conjugation. So we have double bonds on the ends. There's this empty carbon in the middle that has no double bonds on it. Because there is no double bond attached on either side of this carbon, it does not count as a conjugated system. And this carbon also doesn't have any available p orbitals to overlap with the other p orbitals here. If you look at these other examples with the radical or the lone pair or the carbocation, there was always an extra orbital ready to overlap, because the carbon or the nitrogen did not have all of its electrons stuck in bonds like this carbon has here. So when we have 3 or more p orbitals overlapping on adjacent atoms, it is called a pi system. P orbitals are a bit like the rooms. So there's an electron given from each carbon to put into the double bond, and each p orbital only holds up to 2 electrons. So when it comes to naming cycloalkanes and aromatics, benzene is one of the most common aromatic compounds that I've come across. I have a separate video up for when cycloalkanes and benzenes are actually substituents on a chain, something like this, where they're not the main chain. But what if they are the main chain? What if the substituents are directly coming out of our benzene or our cycloalkanes? Let's take a look at this example. On the bottom here, I have a chlorine and an ethyl group coming out of a cycloalkane. And on the top, I have the same groups at the same positions coming out of a benzene. So I'm going to number these counterclockwise because recall that alkyl substituents have a higher priority than halogens. So I will put the ethyl on the number 1 carbon. Now naming the substituents, we have an ethyl on carbon 1 and a chloro on carbon 3. Remember, we have to put them in alphabetical order, and C comes before E. So we have a 3-chloro, 1-ethyl for both of these shapes. But what about the ending? Now the ending is where things change. If the benzene is the main chain, like we have up here, the ending is just benzene. 3-chloro, 1-ethyl benzene. But if we have something like this cycloalkane, This is a 6-carbon chain, and when we name cycloalkanes, we put the word cyclo in front and name the regular alkane, and in this case, a 6-carbon chain would be hexane, but because it's a ring, it's cyclohexane. 3-chloral 1-ethyl cyclohexane versus up here, it was 3-chloral 1-ethyl benzene. Naming benzenes or cycloalkane is almost the exact same as naming regular alkanes, except the ending is not just alkane anymore. It changes to be either cyclo with the alkane name or benzene.
When two cyclic compounds become fused together, it is called bicyclic. This can be done in 3 different ways. Let's start with the first one, fused bicyclic compounds. When we have 2 rings fused together, these carbons are overlapping. These are called the bridgehead positions, and these will be the 2 shared adjacent carbons. Then we have the bridged position. This is almost the same as the fused compounds, but there is a bridge that consists of more than 1 carbon connecting 2 cyclic compounds. For example, this is the top view, and this carbon is a part of the bridge. Let's look at what the side view would look like. This side view shows this top carbon and these 2 other carbons in the ring as being right here. And this is still a 6-membered cyclohexane ring, just seen from the side view instead of the top view. So there will always be at least 3 carbons shared. Sometimes we can have more than that. For example, the bridge might look something like this, where you have 2 carbons that will be shared instead of just 1. Then we have Spiro bicyclic compounds. This is when there is 1 carbon connecting the 2 rings. This is the fused carbon that causes it to be a Spiro bicyclic compound. Let's look at some examples of how to name these compounds.
When we name fused and bridged bicyclic compounds, they almost follow the same rules. The first thing we do is number around the shape, counting every carbon along the way. These 2 rings consist of a total of 10 carbons, so we name this as an alkane. The prefix for 10 is dec, and we put ane at the end to give us decane. Because it's a bicyclic ring, we put bicyclo at the front. And then we have square bracket, where we will leave 3 empty spots with dots in between. Inside these brackets, we are going to count the number of carbons on the left ring, the middle, and the right ring. On the left ring here, we have 1, 2, 3, 4 carbons. We don't count these fused carbons. On the right ring, we have 1, 2, 3, 4 carbons as well. In the middle, we don't have any carbons, so we will put a 0. This is because we don't count the fused carbons. If we had a shape that maybe looked like this, we would have 2 carbons in the center. But without counting these fused carbons here, there's nothing in the center, so we put a 0. So this shape is bicyclo 4.4.0 decane. Now let's see what the difference is when we name a bridged compound. Once again, I'm going to number around the shape, and I have to count these carbons in the center. This is what the side view would look like. We have 1, 2, 3, 4, 5, 6 carbons around the ring, and then these 2 bridged carbons. Both of these shapes are indicating the same compound. This is the top view, and this is the side view. Now, naming this bridged compound, we have 8 carbons overall. So just like we did with the fused compound, we will name the 8 carbons as an alkane. The prefix for 8 is oct, and naming it as an alkane gives us octane. We put bicyclo in the beginning, and we leave 3 spaces separated by dots. Now we count the carbons on the left of the shape, not including these top and bottom fused carbons, carbon 1 and 4. On the left and on the right, we have 2 carbons each, carbon 5 and 6 and carbon 2 and 3. And in the center, we have carbon 7 and 8. This gives us bicyclo 2,2,2 octane. Now let's name a Spiro compound. These compounds
are fused together with one common carbon. To name these, we put Spiro instead of bicyclo in the beginning, and in the brackets, we have only 2 empty spaces instead of 3, still separated by a dot. The total number of carbons in the shape, including the fused carbon, just like before, is 8, so we name it as an alkane, which is octane. Now we're going to put the number of carbons in each ring, not including the fused carbon. Carbons 1, 2, 3, and 4 are in the left ring, and carbons 5, 6, 7 are in the right ring. This respectively gives us 4 carbons and 3 carbons. So we have Spiro 4,3-octane. So that's the end of today's lesson. If this video helped you, please give it a thumbs up and subscribe to my channel. I will leave a link in the description below to the related blog post for more information regarding this topic. Thanks for watching!